All right, everybody. So today I was going to give out some Skittles, bummer. But maybe we can do it later on this year or something. But everybody knows that red and grape Skittles are the best Skittles, but this is actually a true story. The last time I got a fun-size bag, there were no red Skittles in it. Super bummer, right? So the bag was manufactured at the Skittles factory where 10,000 Skittles are made each hour. And then 20% of the Skittles are supposed to be red. To make a fun-size bag, 10 Skittles are chosen from each bag. What are the chances of getting a fun-size bag with no red Skittles? So that's the big question, right? What are the chances of getting a fun-size bag with no red Skittles, right? First and foremost, we should check to make sure this is binomial before we can use our binomial formulas, right? So we need our bins. Can't tell, that's going to be something that pops up on a test. Well, here you go, right? So you're either red or not, so it's binary. Independent, well, it says to make a fun-size bag, 10 Skittles are chosen for each bag. Is this independent? I don't think so. We are not replacing the red Skittles, right? Or any of the Skittles at that bet, right? We're choosing 10 Skittles. If we're not replacing the Skittles, that means the probability changes, right? So we're really breaking independence and the same probability piece there, right? So this is a no, not binomial. But we still can find the probability of getting 0 red Skittles in a group of 10 from the factory. If this is not a binomial setting, though, we're going to have to do this the hard way. So if 20% of the Skittles are red, that would mean 8,000 of the Skittles are not red, right? Out of the 10,000. So I have 8,000 choices out of the 10,000, right? And if I draw one non-red Skittle, that leaves me with 7,999 left out of 9,999, right? And then we have 7,998 out of 909 or 9,998, blah, 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 all the way down to the 10th Skittle. So really, this is the chance of getting no red Skittles in that situation out of the 10,000 Skittles that were made in that factory that hour, right? So find the probability of getting no red Skittles in a group of 10 from the factory if this was binomial, right? So if we were going to show our work, we could either do this with I have 10 and I'm choosing 0 reds. So the probability of a success, I'm having 0 successes and I'm having 10 failures, right? Or I could use my binomial PDF because we're looking for a precise number of Skittles. The number of Skittles is 10. The probability of getting a red is 0.2. And the X that I'm choosing is 0. And what you're going to find is when you do this calculation, you're going to get this value right here. Notice how infinitely close numbers 2 and 3 are, right? So these are basically the same. So removing the Skittles, the 10 Skittles, I should say, from a very large sample was not detrimental. So it really didn't change, that idea of same probability. It didn't really change things that much. And we're going to talk about this shortly, but this gets to the idea of the 10% rule. So if you don't have independence, you can check the 10% rule, right? Okay, moving on. To ensure that I get more red Skittles, I buy a jumbo bag instead, right? That would be the smart thing to do. So the jumbo bag contains 900 Skittles. Let X be the number of red Skittles in a bag of 900 Skittles. Use a binomial distribution to model the situation. So if X is the number of red Skittles in a bag of 900 Skittles, to find the mean and the standard deviation of X, remember our mean formula from yesterday was n times p, and the standard deviation is the square root of n times p times 1 minus p. So the mean is equal to 900 times that 0.2. So the mean of X is equal to 180 red Skittles, right? And then the standard deviation of X is equal to the square root of 900 times 0.2 times 0.8. And when I calculate that, I get the square root of 144, which gives me 12 red Skittles. This little x tells me that I'm talking about variable x, just as an FYI. So what's the probability of getting at most 150 red Skittles, right? So we have the probability x is less than or equal to 150. We can use, remember with inequalities, it's cumulative. We can use binom CDF because we're looking to accumulate data, right? And we know our n is 900, our p is 0.2, and then this time that x value is 150, because usually when we're talking about a distribution, remember we're talking about what's to the left, what's shaded to the left, and then our center was 180, and this is a binomial distribution where n is 900 and p is 0.2, right? So if we were to actually calculate this out in our calculators, you would get 0.006. At most 150 red Skittles, so more than likely I'll end up with more than 150 red Skittles, right? If I were to make a histogram of X, what do you think the shape would be? Well, the larger and larger the sample size, the better and better of an approximation we should get, right? So the idea is you should end up becoming approximately normal. And this is the idea of the large counts rule. Which we'll talk about on the other page. So remember, there's the 10% rule and the large counts rule, right? The 10% rule up here, the large counts rule refers to this, right? So the larger and larger the sample we get, the more normal it should be. So we're going to try this with a normal distribution. Remember, normal distributions are described by mean and standard deviation. The mean of a distribution is 180, and the standard deviation is up here. We just calculated it, 12, right? So we have 180 and we have 12. So if I have 180 and it says we want at most 150, so I could use, in order to do the probability that X is less than or equal to 150, I could use norm CDF. And then remember, you have your lower, your upper, your mean, and then your standard deviation. So we have negative infinity as my lower bound, 150 is my upper bound, my mean was 180, and my standard deviation was 12. And you're going to get a value of, how about that, 0.006. But remember, this only works when you have a large enough count, so large enough sample size. I do want to practice something a little extra though. So I want to do the same problem again. You know how it said at most 150 red Skittles? I want to go with at least 150. And then we're going to do it with binomial approximations. So when you're talking about at least 150, remember that's 150 or above, right? So if we do at least 150, isn't that the exact same thing as 1 minus the opposite of being less than or equal to 149, right? So think about it. If I want to be at least 150, I could just take away 149 and below, right? The reason I have to do this is binomial only goes to the left. It's not like your normal distribution where you can choose your boundaries differently, okay? So if you are doing binomial, you have to do 1 minus, and then you'd have to do binom CDF with your NPX, where your N was 900, your P was 0.2, and your X, in this case, is 149. Hopefully that makes sense. And then, yeah, you're going to get 0.996 in this case. But anyway, let's get to the important ideas for today. So in order to use a normal approximation to approximate a binomial distribution, we have to have a few conditions that work. One thing that's called the 10% rule for independence. So if you fail the independence, then you can always try the 10% rule instead, right? And the rule says when we have a random sample N from a population, which is size is capital N, we can use a binomial probability calculation if the sample size, remember lowercase n, is less than 10% of the population size. That basically means that your sample is small enough, so if you take it out and don't replace it, it's not going to affect the probability a significant amount, right? Then there's this idea of this large counts condition. And this one helps us with normality. So we can use a normal distribution to model and approximate a binomial. Setting. If, and then the check that we can do for normality here, once again, is if n times p is greater than or equal to 10, and if n times 1 minus p is greater than or equal to 10. This is basically saying that you have at least 10 successes and at least 10 failures. And the idea is that you have to have a good enough sample size in each category in order for this to be considered something that might be approximated by a normal distribution. Okay, I'm going to go through and check your understanding, and then we'll check our answers. All right, so first question was asking you to check your bins, and independence fails. But remember, if you are failing on the independence thing, you really just need to check to make sure you have a sample size that's not too big where it's going to affect the probability in the long run, right? Problem 2, you're going to have to use binom CDF. Remember, you're accumulating. Number 3, the reason you're able to approximate using a normal distribution is you have a good enough count. And then for number 4, in order to use that normal distribution, remember you have to find the mean and the standard deviation. This is something that we learned how to do in 6.3 day 2. And then you can take a look at all of my work. This would get you full credit on a test or a quiz. You might have to do this on a test. Cough, cough.